linear equations. Okay, so in math 336, I think it's called. Differential equations, I think here. Anyways. Okay, so you learn 254? Yes, 254. Okay, so in math 254, you learn, you spend this whole semester talking about techniques to solve differential equations. So this technique is the most difficult technique that you learn here. So that's it. Finito. So there's much more to learn, but you'll do that in the next class. So the purpose of learning differential equations now is just to get a feel for what they represent and what their solutions look like, and sort of just to get you started on solving them. But the real meaty stuff comes later. Yeah. So,
putting the stuff in?
What is it?
It's redundant. Read it twice.
Well, sometimes you need to see things twice so that it sticks. Anyways, okay. So what do they look like? So take a differential equation. That looks like. So it has to be first order and linear. So let's say you have, so we'll write it, let's see, how about, okay. So let's say we have y prime plus, let's see, give me a, so let's say there's, okay, let's do a of x, lowercase a of x, y prime, plus b of x, y. And then this is equal to, let's say, c of x. Okay. So this is, it's linear and it's first order. What would make this into a second order? So why is it first order? What makes this? Yeah, we only have the first derivative, right? If we had y double prime or the third derivative, then it would be second or third order. And then what makes it linear?
That there's no powers, no exponents, or no.
Yeah, so all you have is products of functions of x with y's and its derivatives. So in this case, it's first order. So if, for example, so tell me something simple that I could do to make this not linear. What can I add in there? Yeah, if I add in a y squared, for example, then this is no longer linear, right? Because we have that quadratic term. Okay, so this method only works for linear first order equations. Okay, so now the first thing we do is we have to put it in standard form. So in standard form, and so it looks like y prime plus a, capital A of x this time, y equals to capital B of x. So these are the letters that your book uses, so I'll just use those two. Okay, so now if you have, in some other form, what do you do to put it in standard form? So like, for example, if I just take the first one, the first equation that I just wrote down, how do I go from the first one to the second equation? Yeah, divide by. Yeah, right. That's the only difference. So if you have something multiplying the y prime, so basically you want y prime to have nothing, no function in front of it. So if it does, you divide through by it, and then that's putting it in standard form, and then you have the function, some function of x on the right side. Yeah.
So the A and B are shifting to the right. Is that what happened?
No, these are completely different a's and
Oh,
b's.
that's
So
what I got.
yeah,
Okay.
yeah.
What if you divide by that ax?
Yeah. So to get to this, you basically So let's put it right here. Divide by a of x on both sides, right? So here, these could be anything, just generic functions, a and b. Right? So this a and this b do not necessarily have anything particularly important to do with capital A and B. Okay, so the idea is this, and it's it's not something that you would really think about, but the idea is a little interesting. The idea is that you suppose there was some magical function, alpha of x, we'll call it. Some magical function such that what do we want this magical function to do? So the idea, let me actually, I think, let's leave a little blank here. So we're going to fill that in, but I want to show you guys sort of the idea. So it's one of those things that it's not something that you kind of think, oh yeah, of course I could have thought about that if I thought for a little bit. It's one of the things that you're like, what? Why would you ever do that? But it works. So we're going to multiply through by alpha of x. So we're going to leave a little space here, and we're going to multiply. We're going to multiply by magic. Yes. Okay, so you multiply through. So, you get alpha of x y prime plus alpha of x a of x y is equal to alpha of x b of x. And so you kind of look at the left side, and it looks kind of interesting. A little bit interesting. Not super interesting, but let's suppose, okay, so I'm gonna take, so I'm not really going to tell you where this comes from, but I'm going to rewrite the left side, and I'm going to rewrite, so I'm going to substitute, instead of alpha of x, a of x, I'm going to put alpha prime of x, and then y is equal to, so the right side I'm just going to leave alone. Okay, now, if you take a look at the left side and you think back to the rules of differentiation, what does that look like right there? Looks like the product rule, right? Doesn't that look like the product rule? First function derivative of the second plus derivative of the first times the second. That's just the product rule. Okay, so, all right, so for the left side to be the product rule, then this magical function that we're just inventing right now, that we just made up, totally made up, it has to have this property, right? That you have to be able to go from here to here. So you have to be able to, so that's why I left the blank here for the such that. What we need is for alpha of x, a of x, to equal to alpha prime of x, right? Do you guys agree? So for us to be able to go from this equation to this equation, this has to be true, right? So this magical function that we still don't know what it is has to have that property for that to work. Now, and then we ask ourselves, okay, so why does that help us? Well, so let's leave this whole idea of what this function actually is for a moment, and let's just say we're trying to solve this last equation that we have here. So if I want to go backwards from the product rule, what would this look like? Before I expanded it.
The alpha x times y.
Mm-hmm.
Root of
Alpha of x times y, all of that prime, right, is equal to just the right side, just leaving it alone. Okay, and then now you look at this, and what can you do to get rid of the prime? Integrate both sides, right? So we integrate both sides with respect to x, right? So we should write this down. So we integrate both sides. Okay, now what do I get on the left side? Alpha of x times y is equal to this integral, right? So the integral of alpha of x b of x dx, and I just leave it like this. Okay, now here this is a be careful moment here. So let's now. So I can solve for y easily here, right? So how do I solve for y? Yeah, just divide by alpha of x, right? Okay, now, all right, so we divide by alpha of x, and so I have the integral of alpha of x b of x dx, and then over alpha of x, right? And we still don't know what alpha of x is, right? So that's fine. We'll deal with that later. Now, you have to be careful right here. So be very, very careful with the constant of integration. So this can be easily, you can easily make an accident here because you get the integral, right? And then you have the plus c, right? But what's true about the plus c? The constant has to be so like would this be okay? So like let's say I were to break this up and then put a plus c.
No, it has to be part of the numerator.
Yeah, it has to be. So this constant has to also be divided by alpha. So it's just something that you have to be careful with. So the plus c. So what we'll do is we'll just for emphasis to make sure that we don't mess it up, we'll put the plus c right there, so that we remember that the constant is going to be divided by alpha of x. Okay, so you just have to be a little bit careful with that. Okay. So this is my solution. That's the solution. This is the solution to the differential equation. Now, I don't think that really gave you much because, well, you have this magic function that we still don't know what it is, right? So it's like, okay, so because we said, basically we said, okay, well, if this function exists, if I can imagine some function that has this property, then it all works out nicely and I can go home happy, right? But then you have to go back, okay, well, can you really come up with this function, right? So that's the question that you have to go back to. So we know that this is what we want, right? So we want alpha of x to satisfy this.
So we solve the differential.
Yeah, so we find it, right? Okay. So let's find alpha. So this is alright. So I'm gonna move my board over. Can you guys remember this? Alpha. I want alpha of x, a of x to equal to alpha prime of x. Okay, you guys got it? It's in the brain. It's waiting there to be solved. Finding magic. Okay. So what was it again? You guys said you remembered.
Alpha x, a of x.
Okay. All right. So let's rewrite it. So this is a differential equation, right? So how can I rewrite the left side so that it d alpha over dx. Now, what kind of differential equation is this? Separable. Okay. And, well, I'll just leave it like this. Okay. So it's separable, right? Separable. So how do I solve that? Well, I just move all the alphas to the left. Dx to the right, right? So it's separable. So then I have d alpha over alpha. I'll put alpha of x is equal to a of x dx. Okay, and then what's next? Integrate both sides. So integrate the left side and the right side. Okay, so what do I get on the left side? Okay, so natural log absolute value of alpha of x, right, is equal to, we just leave that alone, right? The integral of a of x dx. Okay, so then what is alpha of x equal to? Yeah, it's just e raised to that power, right? E raised to the integral of a of x gx. And so this is it. So, okay, now my recommendation is to simply remember this. This is your magic, and actually it's not really called magic, I just made that up. But this is really called the integrating factor. So remember this, and then remember the process that we went through to solve it. So we multiplied through, right? Wrote the left side as using the product rule. We went backwards, integrate both sides, and then that's it, right? Divide through by what you get. So you don't want to do it by memorizing the formula because, you know, it's just a formula, and then later you'll forget where everything came from. So you don't really want to memorize this. All you need to remember, make sure you remember the integrating factor, and then remember everything that we did here. You multiply through. The left side has to be a product rule. You have to be able to go back and rewrite it as a product rule. And then integrate both sides, divide by the integrating factor, and then thumbs up, you're done. Right? Yeah. So
the orange square was the integrating factor? I can't.
No,
The last part.
the purple. Yeah. And what's the something else that's really important that you have to remember to do? You have to make. Well, yeah, that's important, but that'll come also if you do it this way. It'll you should have no problem getting the C right. But something else is make sure before you do all this that it is in that it's in standard form, right? So you have to make sure that there's nothing multiplying the y prime and the y have to be on the left side, function of x on the right side, and because otherwise then it won't work out. Okay. All right. So you guys want to do an example? Okay. So let's see here. Example. Say we want to solve. You guys want an easy one or a hard one? X squared y prime plus 2xy equals to cosine squared x. All right. So, what do I do first? Okay, so put it in standard form. So we put it in standard form by dividing through by x squared. Okay, so then I get y prime plus, what is that equal to? 2 over x times y is equal to cosine squared x over x squared. Okay, and then what do I do next? Ooh. Okay, so I need to find what alpha is, right? So find my magic function or integrating factor. So e to the integral of a of x dx. So what is a again? So alpha of x is equal to e raised to the integral of a is this function that's multiplying y, right? So 2 over x dx. And then notice that if I wouldn't have put it in standard form, this would have been a completely different function, right? I would have been trying to do the integral of 2x, which of course is very different from 2 over x, and it would have given me a completely different result, right? And it wouldn't have worked out. So if you'll see when you keep going, when you get to the point where you have to do the product rule backwards, you have to make sure that that's actually a product rule backwards. If it's not, then that means you made a mistake, because it always has to work out. Okay, so e to the integral of 2 over x, which is equal to e to the 2 natural log of x, right? And what is that equal to? X squared, right? So this is this is e to the ln of x, and then squared, right? Which is just x squared, right? Okay, so then we multiply by alpha of x, which is x squared, right? So we multiply through, and when we multiply through, I get
Do we get any alpha?
yeah, so it just has to be 1. So of course this is plus or minus, right? But we only need 1. So this is x squared y prime plus, what would I get? If I multiply this by x squared, I would get 2x times y, and that's equal to cosine squared x, right? Okay, and then on the left side, do I have a product rule? Yeah, I do, right? So on the left side, so we'll do a backwards product rule on the left. Okay, so let's go down there a little bit. So if I write that as a product rule, it's equal to the derivative of x squared times y, right? Because so I have the first times the derivative of the second, which is that, right? And then plus the derivative of the first times the second. You guys with me? Yeah? Okay. So this is equal to cosine squared x. And then? Integrate both sides. So I integrate the left side and the right side with respect to x, right? Okay, so then what do I get on the left side? X squared times y is equal to the integral of cosine squared, which is, what is that?
1 over 2x.
So let's do this. So cosine squared, remember, is 1 plus or minus?
It's plus.
It's plus, yep. 1 plus cosine of 2x all over 2, right? So if I get the antiderivative of that, that would be 1/2 x, right? And then
1/4.
plus sine of 2x over 4, and then plus c. So notice this is, so we have the plus c, right? And then now here, then we divide by x squared, right? And so notice we'll have the x squared under the constant c. So we've got, and solve for y. Okay, so then we get, so y is equal to, if I divide by x squared, what does this one become? 1 over 2x, right? Plus sine of 2x over 4x squared plus c over x squared. And then what? You're done.
How come it's not minus sine?
Because it's the antiderivative of cosine, so the derivative of sine is positive cosine. All right. Questions? Questions? No? You guys like first order, linear first order differential equations? Does it seem too easy? You guys think I'm trying to trick you? All right, let's see. Let's try another one. Let's do one with some initial conditions. How about 2xy prime plus y equals to 6x, assuming x is positive, and y of 4 is equal to 20. Okay. Let's see. Alright, so off we go. What do we do? What is it? Oh, standard form. Okay, so divide everything by 2x, right? So I would get y prime plus 1 over 2x. Y equals to, what do I get on the right side? 3. Okay. And then find alpha, right? Alpha is e to the 1 over 2x dx, which is, oh, this isn't a very good one, is it? All right, so what is this equal to? So e to the 1/2 natural log of x, right? Which is, what does that turn out to be? Square root of x. All right, so then I multiply through, right, by square root of x, and square root of x. So then I get square root of x, y prime, plus square square root of x. Well, if I multiply that by square root of x, this one, what would I get? What is that equal to? If you multiply this by square root of x. 1 over 2 root x, right? Yes? No? Good. What's wrong? So we multiply by... Right? Okay. Right? Uh-oh. You guys are worrying me now. You guys need to get some coffee or something? Okay, so then what is the left side equal to? Is that equal to product of two functions? Derivative of the product of which ones? Square root of x and y. Right? It's always a good idea to check. So that's definitely the same, right? So this is equal to 3 square root of x. Integrate both sides with respect to x. And then we get, so square root of x times y is equal to, what's the antiderivative of?
No, 2 times x to the 3 halves. Oh wait, no, 2/3 x to the 3 halves. I'm sorry.
2/3. Yep. X to the 3 halves, right?
Times 3. Yeah.
Okay. So let's get rid of those 3's there. Oh, how many crickets? All right, and then what are we forgetting?
C.
Plus c. And then okay, so this time though, we have some conditions that we need to satisfy, right? So we know that y of 4 is equal to 20. So that means that I'm able to find what c is, right? So I plug in 4 for x, right? 20 for y, and that'll give me c. So what do I get on the left side? 40 on the left is equal to 4 to the 3 halves is 8 times 2 is 16 plus c. So this means that c is equal to 24. And so my solution, if I grab, so this is what I had, right? Ooh. Hello. Okay. Hey. Okay, so this is what I had. If I divide by root x and I use plug in 24 for c, then I would get that y is equal to 2x to the 3 halves plus c is 24, right? Divide that by square root of x, and I can simplify that into 2x plus 24 over square root of x. And that's it, right? Questions? Yes?
When you do the e to the integral, I forget what this was.
The integrating factor?
Yeah.
Yeah.
What is my c? Do I not have c in that situation?
Yeah, you don't have to worry about it because then, so you only need one integrating factor to make it work. So you don't have to worry about, all the different cases. You only need one. And so, you get to pick. You're creating it. You're making this up. So you create this function that when you multiply through, it gives you the exact situation that you're looking for. There's no point in doing another one. It's like doing the problem all over again.
One other thing, why didn't we divide the c in this one by?
We did.
Okay.
What we did is that we could have divided by by root x here. But instead what we did is, before we did that, we plugged in the conditions that we were given so that we could find what c is and then divide by root x later.
That's the only reason we did that.
Yeah. You could have divided by root x. The thing is that it's usually easier to leave it alone, leave it in this form when you're finding the constant, just because you eliminate a fraction, and so it just makes the calculation a tiny bit easier, but you don't have to. If we would have divided by root x, then we would have gotten a fraction on the bottom. We would have had to move it back again anyway, so